Hello, and welcome to the seminar, the Essex seminar today. Just a heads up that this meeting is being recorded for people who want to see it later. Um, so this is a seminar as part of the Essex CalVal Affinity Group here at the University of Maryland. Um, I'm pleased to invite today Eric Norrgard from NIST. Eric is a physicist in the fundamental thermodynamics group at NIST. He received his PhD uh, from Yale University in 2016, where he performed many of the first demonstrations of laser cooling and trapping of molecules. His research highlights include the first laser slowing of a molecular beam, the first magneto-optical trap of a molecule, and subsequent thousand-fold improvement in trapped molecule phase space density with now with a novel time-dependent trap. His postdoctoral career included development of the Centrix experiment towards measurement of the shift moment of a thallium nucleus and development of a pressure sensor and standard based on cold atoms. As an NRC postdoc fellow, he conceived the platform realizing the integrated molecular experiments at NIST, which will allow for trapping of molecules in record number for precision metrology and numerous other applications. His current research involves using atomic and molecular systems as quantum sensors of black radiation, voltage, RF, electromagnetic fields, and more. So yeah, I think we'll all be very curious to know more about how this current technology Eric's developing could be used for improving thermometry and sensing of blackbody radiation for the for remote sensing in atmospheric sciences and other technologies. So whenever you're ready, Eric.
Okay. Thanks, Peter, for that.
I'm sorry. And one more point is if we'll have a Q&A at the end, and if anyone wants to ask questions in the online portion, they can ask questions in the chat, and then they'll be answered at the end. Thank you.
Okay. Thank you, Peter, for that introduction and for the invitation to speak here today. The title of my talk is Blackbody Radiation Metrology with Atoms in a Vapor Cell. And so recently, I was doing some training on getting, funding various grant agencies, and I heard that if I just put generative AI in there somewhere, it's going to increase my chances. So I fed my talk title into an AI algorithm, and this is what popped out. Okay, so this apparently will explain my entire talk, and if you want to leave now, you can, but I'd ask you to stick around if you want some words that go along with it. Okay, blackbody radiation metrology with atoms in a vapor cell. This project is a collaboration between teams at NIST Gaithersburg, which is right up the road from here. It's where I work with Stephen Eckel and our postdoc David LaMantia, and NIST in Boulder, Colorado, led by Chris Holloway's group in RF fields. Okay. At NIST Gaithersburg, I work in the sensor science division, and our division's mission is to maintain and disseminate standards for 3 of the 7 SI base units. There's the Kelvin, the meter, and the candela. And sensor science has approximately 100 scientists. There's all sorts of research projects and calibration services that are going on in the division. So I don't have time to tell you about everything that we do, but just to highlight an example from each of these 3 SI units, there's work going on developing chip scale thermometers that are entirely photonics based. In the dimensional metrology group, They've done some work doing measurements that were critical in terms of getting the James Webb Space Telescope operational. And then the NIST STARS program is a program to catalog standard candles for various reference calibrations. So I'll talk a little bit about NIST's work in radiometry. And so the idea here is probably very familiar to a lot of the audience. The best electromagnetic field that we know how to make today is blackbody radiation. So you can use that to calibrate all sorts of instruments. And the way that you do that is very simply, you make a black box with a hole in it and measure its temperature. And then Planck's law will tell you from the temperature something about the radiation spectrum coming out of that instrument. And then, there are various details of making better approximations of that. So NIST has blackbody sources that are optimized for calibrations in the microwave regime, ones that are optimized for low temperature. If you have something that you need calibrated, but you can't send it to NIST, we have a transfer radiometer that can be sent to wherever you have a device that needs to be calibrated. So NIST has done some work on the past with, for example, the CoBRAS instrument is manufactured at L3 Harris. And so at the Harris facility, they have this external calibration blackbody, external calibration target that they use for calibrating, and they want to have some sort of validation that their calibration is correct. So we can send a transfer radiometer to their facility and see how they agree. So to make a long story short, because I was not involved in the taking of this data, they do agree to within their with their uncertainty. So that's some validation that not only is the device working properly, but that that both their and NIST's estimates of the uncertainties of their respective devices are approximately correct. Now I'll talk about thermometers, and we'll keep it very simple to start. You've got your contact and your non-contact. And a contact thermometer is going to work by thermalizing with its environment, whereas a non-contact thermometer is going to sense something about the ambient blackbody radiation and from there infer a relevant temperature. And you're all probably familiar from your everyday lives, if not your professional lives, that the contact thermometers are just much more accurate and robust, right? If you take a non-contact thermometer reading, whether you want to go to work or school that day is probably going to tell you whether you trust the number or you want to take another measurement until you get the right number. That tells you about the level of accuracy that you can trust these things, at least in the medical grade, which suggests that perhaps there's some room for improvement on the non-contact side, at least. There's lots of reasons why you want to measure something without touching it, right? Like it could be really hot, we could be worried about communicable diseases, or maybe the thing that you want to measure is just really far away. And so that's, the bread and butter here at ESSEC. So I'm an atomic physicist, right? So I'm going to greatly simplify my my explanation for remote sensing, so you can see how I view what you guys do. Okay, so there's a source of thermal radiation, and then you're going to get a detector. And on the ground, it might look like one of these devices here that you could get commercially. You're probably going to do some things to make it good for space flight, but at the end of the day, it's basically going to be a pyrometer, a bolometer. And you're going to put some optics in front of that, but we'll just skip those. But then you want to make sure that you know how to convert the signal from your detector into a power or a temperature or whatever. So you're going to have an onboard blackbody reference. And you need to use Planck's law to tell you something about the light coming out of that. So you're going to put a thermometer on your black body. If you want to do that right, you might put a second thermometer on there to look for temperature gradients or for redundancy or so on. And then your detector is going to periodically look at the Earth or whatever you want to look at, and your reference and calibrate and go back and forth between sensing and calibration, sensing and calibration. You might want another black body on there for redundancy, or maybe for another part of the electromagnetic spectrum. And then, of course, these black bodies need to be carefully engineered, have the right geometry to trap the light. You need to paint it with a very special black paint. And all this engineering that goes into these reference black bodies. And then you can use that to calibrate your target, right? But things sometimes go wrong. So this is a story that you can glean from this conference preceding paper. Listed here at the bottom, there's a group at the Space Dynamics Laboratory that sent 4 platinum resistance thermometers to NIST to be calibrated. And so NIST calibrated these thermometers. They agreed within 10 millikelvin. And we shipped them back to Utah, and then they get mounted onto their reference black body, and then they measure, do they agree? And they don't. This plot here is showing that if you take 3 of the 4 thermometers and subtract off the 4th one, they disagree by as much as 200 millikelvin over the relevant temperature range. And so the question is, well, did NIST do a bad job of calibrating these? And the answer is no, of course not. But PRTs are very sensitive to lots of environmental factors like vibrational shock. And much to the chagrin of these individuals, that if they couldn't survive ground shipping across the country, how is it going to make it up on a rocket, right? So these things, the calibration depends very sensitively on how the thermometer is treated, I guess. And to make matters worse, if you wait a year, the response will drift by some amount that might be on the order of 10 millikelvin, okay? That might be a small amount, but if you're looking at things like climate change, that might be a substantial amount in 1 year for what you're trying to measure. So the question is, can we get to a point where we totally bypass these calibrations and relying on the thermometers for remote sensing and thermometry applications, and use something like an atom that never needs to be calibrated? An atom has its properties defined by fundamental constants, and so they should never change. They should be constant, right? So if you have an atom interacting with blackbody radiation, there's 2 potential effects. One is state transfer. So let's imagine it only has 2 quantum levels, but there could be more. And the atom has, all the atoms in your ensemble have a population in one state. Blackbody radiation is going to drive population to another state. And you can either look at the steady state of the atom in thermal equilibrium with the blackbody radiation field, or you can look at the dynamics as you actively change something about your system while it's interacting with blackbody radiation. But something about the way that the states get transferred in the presence of BBR can tell you something about the strength of that field. And then the second effect is the frequency, or sometimes called the Stark shift. And here, if you think about the composite quantum system of the atom plus the light field, the eigenenergies of that will change in proportion to the strength of your blackbody radiation field. Turns out that this effect is quite small. You can measure it in atomic clocks, but that's a whole other type of experiment where you need high sensitivity and need to worry about many other systematics before you get down to the shift. So we're going to focus on state transfer today, but in principle, either of these effects can be tied directly to the SI through the atomic properties and their dependence on these fundamental constants. So if we can engineer a measurement based off of atoms and that doesn't depend strongly on other aspects of our measurement scheme, then we can get what we like to call a primary measurement of a radiometric temperature. And so the sort of tool of the trade is these atomic vapor cells. This is what I typically work with in the lab. They're pretty small to begin with, on the order of a centimeter, or maybe you can get one on the millimeter scale. And it's basically just a glass box that has some atoms in it. It's usually an alkali atom, and those atoms have a not large but substantial enough for our application vapor pressure around room temperature. So there's a gas of basically non-interacting atoms in there. We can probe them with lasers and read out the states of the atom and do all sorts of AMO physics with this little tiny vapor cell package. Of course, once you know exactly what the parameters of your measurement are, teams at NIST have already developed these chip scale sensors that are, sub-millimeter, that are fully photonically integrated. So you can fiberize your entire measurement for light in, light out, other electronic signals that you might want to also have on this chip. And these are already being commercially developed by industry. So you can actually go out and buy one of these atomic vapor cell chip if you so desire. So the platform of these atomic vapor cells is already very well advanced. And that makes it ideal for trying to do sensing applications, because once we develop a new type of sensing modality, we can already build off of these decades of work making these vapor cell platforms. And so the goals here are to do something related to thermometry and radiometry. And the question is, can we go from something like this handheld instrument that might be good to 1 Celsius or so, to a non-contact thermometer that's based on an atom that never needs to be calibrated, or potentially to go from this sort of simplified picture of remote sensing that I showed you, where you're relying on a thermometer to tell you what the blackbody radiation from your reference should be, and instead use an atom to tell you what that blackbody radiation actually is. Or maybe even in the future, can we bypass the detector entirely and use the atoms themselves to do the sensing? So these are the sort of big picture ideas of what we'd like to develop. And so enter the compact blackbody radiation atomic sensor, or CoBRAS. And here's the detection principle. We're going to take an atom, and here I've plotted up all the energies in this quantum system. We're going to use one laser, maybe more lasers, but you can get by with just one. And that's going to excite you from your ground atomic state up to some excited state. And from there, you can absorb a blackbody radiation photon. And then you subsequently will fluoresce 2 or more times to get back to the ground state. And these fluorescence channels will have different wavelengths. Some of them are temperature dependent. So the stronger your blackbody radiation field is, the greater the signal. And some of them are basically temperature independent, and so it will not depend to a great extent on temperature. And so those temperature independent fluorescence channels can be used for normalizing your temperature dependent channels. I'll go into some more details of how that works. But the way I like to think about it is an optical transistor. So you have some laser light, and you want to convert it into some other induced fluorescence wavelength, and it's going to be gated by the blackbody radiation. So the more blackbody radiation you get, the more light out you get. And so this is like a BBR to optical conversion, and the sort of underlying conversion to read out the strength of your BBR field is the rate of BBR to optical conversion. It's dependent only on the radiation temperature and some immutable atomic properties. So that's the sort of an ideal thermometer, right? And importantly, if I circle these other circles are meant to highlight other potential BBR excitations. Each one of these channels has its own unique BBR sensing wavelength, and that wavelength is associated with a detection wavelength, okay? So each unique detection wavelength in principle can be paired with sensing a blackbody radiation channel. And we can also change the excitation state by tuning our laser to make different sensing BBR wavelengths stronger for different kinds of measurements. So that's the underlying principle in a nutshell. Or if you just ask a AI what we're doing, it's something like this. Okay, we shoot lasers at atoms and measure temperature. Okay. So fluorescence thermometry, I'll tell you about two approaches. I'll tell you about this first demonstration we did with Rydberg atoms, and then I'll tell you about slightly less excited atoms where we're doing ratio measurements to read out the temperature. So approach one, we had a Rydberg cesium atom. So if you don't know, Rydberg atom is just an atom excited to a very high principal quantum number. And for the purposes of this talk, 35 is a large number. Okay, so in this example, we used 3 laser photons to excite up to this 35p state. And then we use 1 microwave or RF photon to further excite to this 34D state. And so what we're doing is we're attempting to sense the strength of this RF field. For this example, the RF frequency is about 20 gigahertz. Okay. From the 34D state, you subsequently decay back to the ground state with a couple of colors, and we're going to use some interference filters to isolate the green fluorescence at 510 nanometers. So we're converting 20 gigahertz to whatever that wavelength is, some millimeter wavelength, into 510 nanometers. And it turns out if you tune all of your lasers exactly resonant with the atom, and also the RF resonant with that 20 gigahertz, you get this big fluorescence peak in at that 510 nanometer wavelength. But interestingly, if you turn the RF field off, you stop applying RF actively from your microwave generator, there's still this persistent bump here, right? And so this is, we believe, at least substantially due to the ambient RF at this 20 gigahertz. I can show that another way. If we plot the fluorescence as a function of the applied RF field strength, and then these different colors are increasing laser power, right? You can see as you increase the laser power, the fluorescence increases and then saturates once you have sufficient laser power. But then if you go down to low RF field strength, there's this persistent fluorescence signal. And the question is that due to blackbody radiation? Well, it has to be due to some sort of excitation to that last state. There are other things like collisions, right? Because we have a gas of atoms and sometimes the atoms collide with each other. If you run through the numbers, we should not be dominated by Rydberg collisions. There just doesn't seem to be enough atoms there, but potentially the residual ground state atom population could be enough. Run the numbers on the decay rates. The BBR radiation rate is somewhere on the order of the Rydberg rate and the Rydberg ground rate. And so at least in a substantial part of this is due to blackbody radiation, at least from our initial estimates. Now this isn't really a great thermometer, right? This is a temperature dependent effect, but lots of effects depend on temperature. This isn't really a way to quantify anything about BBR, but it's a step in the right direction. But what we really want to do is use ratios, because when you take ratios of measurements, then a lot of the things that you can't control very accurately can drop out. So I'll give you an example here. Here's like the idealized situation. We'll excite the atom or your quantum system using some laser light. And then from there, you can spontaneously decay one or more times and get back to the ground state. Each one of those spontaneous decay paths in general has its own associated wavelength. From your state that is the excited state of your laser transition, you can excite with blackbody radiation and then subsequently decay. But now this new decay, we'll call this one, we'll pick one and call it lambda 1. This one's only present if the blackbody radiation is present, okay? And so this is a temperature dependent channel, right? So you can only go, you have to go up by being stimulated by BBR in order to go back down. All these other ones in the orange, in principle, will happen orders of magnitude faster due to spontaneous processes than the blackbody radiation stimulated process. And so these ones by orders of magnitude are temperature independent. They're also typically orders of magnitude stronger. So if you take the signal, say I'm now looking at some signal at lambda 1, right? What's going to happen? Well, it's going to be proportional to the number of atoms and maybe the laser power. And then you have to worry about the collection efficiency of your optics at that wavelength, maybe the geometric collection efficiency, or the quantum efficiency of your detector. And then finally, at the end of the day, there's some branching parameter, B, that tells you about the probability to go from this state and then fluoresce at that wavelength. This is the atomic property that we want to calculate. And in principle, it's going to be dependent on temperature. So this is the thing we can calculate that ties us to the SI, and everything else is just a whole bunch of detection stuff that we need to account for and hopefully get rid of so we can have a direct to the SI measurement. So just break it down a little bit by terms. It's basically like the number of relevant atoms in your measurement, some overall detection efficiency, and then a temperature dependent branching factor. So we can help ourselves out by measuring another wavelength. I'll just say that this modality here, where you just sense one wavelength, is basically what that first measurement that I was showing you was, where you look at the 510 nanometer light. You can get some sort of temperature dependence out of there, but quantifying all those other parameters is a bit of a chore. So what we do is we sense another wavelength, lambda 2, and this one is primarily due to spontaneous decay from your excited state. And now you get a whole bunch of the same factors that just depend on this other wavelength, and a different branching factor that again could be temperature dependent. If you take the ratio of those signals, something kind of magic happens in that the number of atoms in your laser power just drops out of the equation. And so if you look at the ratio of these two fluorescence wavelengths, now you've gotten rid of that first term there in the curly bracket. So it doesn't completely make it a primary measurement, but it's closer, okay? So what we're going to do is we're going to take ratios of fluorescence channels, and it can be literally as simple as this photograph here. This is an early attempt. There's a little, I think 2-inch long vapor cell of rubidium atoms, or it could be cesium or some other atom, and you shine a laser through that vapor cell, and you just take a couple of cheap CMOS cameras and look in there with some interference filters. And you can build it up with more accurate detectors or more linear detectors, but in a first go, it could be simple, as simple as this. So it's a very sometimes simplicity is nice in terms of being able to understand what's going on. So here, what I've plotted here is here's like an idealized case, right? And then here's what you would see with a real atom. We're going to excite. This laser excitation is at 360 nanometers for this particular example. So let me explain this plot a little bit better. The blue lines here are the expected fluorescence signal from the atom at the different wavelengths, and including the effects of blackbody radiation. And then these orange lines plotted up top, these are the log derivative of the signal with temperature. So basically, the bigger the orange line is, the more temperature dependent fluorescence at that wavelength is. Okay. And so what you can pick out, if you look at this for a few seconds, is most of the strongest fluorescence channels, like say this one here or this one here, do not have an associated orange line. That is to say, these really strong lines are basically spontaneous decay through channels that don't depend on blackbody radiation. And that's basically what we were expecting, because these are typically orders of magnitude faster than the channels that are only excited by blackbody radiation. And the ones that are very sensitive, like this one or this one or this one here, you come down, there's no associated signal on this linear scale. There actually is a little bump there, but it just doesn't appear on this linear scale. If you look on a log scale, perhaps you would be able to see it a little more clearly. So what that tells you, again, is that the BBR is a little bit weaker than the spontaneous decay channels. But as you turn on the blackbody radiation and make it stronger and stronger, then these channels start to appear more strongly on your detector. And of course, we can get detectors that can look over many orders of magnitude in intensity, so that's not too big of an issue. And now we're using, instead of these CMOS cameras, typically use photon counting PMTs. So this is a spectrum that you would typically look at. And so we're going to pick out, say, one strong transition that doesn't depend too much on temperature, and one a little bit weaker transition that does have a temperature sensitivity to it. And so here's an example for rubidium atoms. Again, there's spontaneous decay, and we can let's pick two spontaneous decay paths, say one at 740 and one at 760. Both of these are basically blackbody radiation independent, so they should be temperature independent. And if we take the ratio of those as a function of temperature, we find that indeed they are independent to within 1% or so. And so that's good. That means that we can predict something about the response of the atoms. It means that if we were to pick one of these wavelengths for normalizing, we know that the ratio of this and something else is not going to depend too heavily on temperature for this one signal. So either one of these could be used for a normalization of a BBR signal. So now we're going to add in BBR excitation and some BBR induced decay. And let's pick one of those BBR induced decay paths. And so a nice one for this example is at 630 nanometers. And we're going to take the ratio of that signal to the temperature independent one at 760. And if we plot those versus temperature, we see this dependence with the data. And the solid line there is our theory. So you can see that it matches quite well. The ratio of these two fluorescence channels agrees with the theory to within 1%. And that's comparable to the x-axis uncertainty in this measurement. There are Y error bars on these that are small compared to the data points for the statistical uncertainty. But basically, to the ability that we were able to measure and set the temperature in this example, we were able to match up the data with our predicted fluorescence ratios. And so all this, so I'll say again, before I showed you the other potential normalization channel at 740 nanometers, and if you plot the ratio of the 630 and the 740, again, it agrees quite well. And so that we have a number of ways to slice and dice our error analysis, and I won't get into all the details of how we do that. But basically, these are the fractional residuals, discrepancy between theory and experiment. And so the typical residual is less than about 1% for all these analysis pathways. Okay, so now I will say that what we would really like to do is I'll go back and say one more thing is this measurement did require us to calibrate our system at one known temperature. Okay, so we had to measure all of the collection efficiency parameters at a given temperature, and then use that to infer the measurement at other temperatures. What we really want to do is get a primary measurement. And so what we'll do is now use two laser wavelengths. One is going to excite to some state that then will have a temperature dependent excitation shown by this blue line, and then decay, and we can measure that fluorescence. But then if we have a slightly shorter wavelength or higher frequency laser, we can excite to some other state that will also spontaneously decay there. And now if we excite using this laser wavelength instead of this one, that same temperature dependent channel becomes temperature independent. And so now we can use that measurement to calibrate the system here, but we don't need to know the temperature. So it's showing you again, this ratio here is going to have two fluorescence wavelengths, 1 and 2, neither of which depends strongly on the temperature. And then if you excite here, 1 depends strongly on the temperature, say this dashed line, but the other one still doesn't depend strongly on the temperature. And so by doing that, and because we can calculate all of these in principle, we can back out what the detection efficiency was when we excite here, and then plug those numbers in here when we do our temperature measurement. So we weren't quite able to do that at our first go with rubidium. We were able to pick these two states. Again, we can calculate the different branching factors for whether we excite to the J 3/2 or 1/2 state. But it turned out that both of these were temperature dependent. So it's basically you add a temperature dependence to this. So, okay, we still need to know the temperature for this next measurement that I'm going to show you, but in principle, we could switch it around and do it in a way where we don't need to know the temperature. So if we just calibrate the branching fraction, or sorry, we calibrate the total detection efficiency of our detectors using the known atomic properties, we get this. Okay, so black line again is the theory, and the dots are the data points. You can see that the trend matches quite well, but there's this overall offset on the branching ratio about 8%. And that corresponds to a temperature uncertainty of about 4%. And again, if we look at our two temperature independent channels, just for another way to look at the data, again, there's an overall offset of about 8%. And the reason for this, we believe, is that in order to calculate what these branching ratios are as a function of temperature, requires us to know, in principle, the coupling of each one of these atomic levels pairwise. So every single line here in this big jumble of lines, we need to know that atomic transition strength in principle with some accuracy. And in general, for these atoms, these transition strengths are only known to about 10% accuracy. There's a few that are known quite well, but there are many lines here that have not been explored very well. And so it's perhaps not unsurprising that our experimental discrepancy is on the same order as the current model uncertainty. And so that opens up this interesting question of who's calibrating whom here. Most of these dipole matrix elements of the atom we know to 10%, but in the lab, we can set a temperature of, with 10 part per billion or better uncertainty. So, these initial measurements seem to suggest that we're now in a position to substantially improve our knowledge of atomic structure in these alkali atoms, maybe by orders of magnitude, by doing these kinds of measurements in a very well-known blackbody radiation environment. And I'll just say that, yes, it would be great if we knew every one of these lines to, 1% or 0.1% or whatever your target accuracy is. That would be the ideal. But we don't even need to go that far, right? Because whatever the uncertainty is, all we care about is at the end of the day is the response function, right? So we can just say, here's a matrix of rates, okay? And we just want, or here's this black box, and we just want to know what the response function of that is. If we can measure that accuracy, even if we don't know the individual transition strengths, because it's an atomic system that's never going to change with time, once we do a calibration of that calibration will never change. So yes, we would like to, we will be able to say something about these various transition strengths, but even knowing it in some, if not by parts, is sufficient for getting a calibration-free measurement with some uncertainty on that. Okay. Okay, so I said we want to do this self-calibration where we don't need to know the temperature. And in our initial step where we did need to know the temperature just because of technical limitations, we're now moving on to doing atomic cesium. And just by property of changing the atom, using the same lasers, we're now able to do a calibration without knowing the temperature. So I'm sorry that I don't have that data to show you now, but that is probably going to be available to us in the next week or so. So that's something that we're very close to demonstrating in the lab right now. And it's just because in cesium, the energy levels are a little bit closer together, so we can get a temperature dependent and a temperature independent excitation with the same laser in cesium. These are all just technical details of what lasers happen to be available, though. So now I'll tell you a little bit about the detection bands. So in this initial measurement that I showed you, where we agree with the theory at sort of the 1% if we can calibrate, or 4% if we just believe our current model of the atom. The Blackbody radiation wavelength relevant here is about 12 microns. So this is where we're sensing right now. If you're willing to change your atom or your laser, these are the wavelengths that are readily available to sense. So again, this was just the one that we were able to do immediately, but there are other ones that are available if that's of interest. And that happens to be in line with a lot of remote sensing bands. So here's a table from the Veers. And again, if you look at their uncertainties, we're already approaching those kind of temperature uncertainties in the lab with these measurements that we're doing now. So that I think there's a lot of promise in terms of getting it to as good as or better for than is needed for a lot of these remote sensing applications in the near future. The other thing is I'll tell you a little bit about, again, there's the contact and non-contact thermometry. And again, this is just a current vapor cell limitation is we're measuring at 12 or another band that we can look at in the near future is 8 microns. For a typical fused silica glass, which is a common material to make these vapor cells from, the transmission window goes up to about 2 microns. And from there, the glass basically will absorb. So in these, in the data that I showed you, all those measurements were basically measuring the blackbody radiation emanating from the vapor cell, from the glass of the vapor cell. So the vapor cell thermalizes with its environment, and then that's what we're actually measuring. If you want to measure radiation, from ambient, from beyond your vapor cell, then the vapor cell needs to be transparent. So maybe a next step in pushing out that wavelength window is to go to a sapphire cell construction. And there we can measure, say, 4.5 micron wavelengths. And so that's something that's commercially available as well. It's not a standard, but it's not an engineering project. It's just a few more dollars to get one of these sapphire constructed cells. Okay. From there, there's other options, standard things like zinc selenide or magnesium fluoride. The point is there are many materials to explore if you want to look at ways to get sensing from other wavelengths and push that transmission window out. And then another thing that we would like to look at is extending the temperature range. So in this first demonstration, we went from basically a little bit above room temperature up to about 70 degrees. And that was just basically the range over which we could accurately heat and control the temperature of our cell. Over that range, we're good to about 1% or better in terms of our agreement with theory. But what could go wrong? Well, I already hinted a little bit with the Rydberg atoms that we were worried about collisions. So one would expect as the atoms get hotter and more energetic, and also as you heat them up, there will be more atoms, there will be more and more collisions. And so at some point, we haven't, or if we get to higher accuracy, maybe we can sense those rare collisions within our experimental uncertainty. So at some point, we're going to have to worry about collisions. And this is a thing that we can tune around. So basically, this is a plot of the relative probability of a collisional excitation that would mimic a blackbody radiation excitation. And that's as a function of the sensed blackbody wavelength. Okay, so in our initial test here, in some units, it's about 0.001, but because of the exponential nature of this part of the Boltzmann distribution, if we cut the wavelength in half, we can gain 2 or 3 orders of magnitude in likelihood of collisional excitation. So just by changing around the properties of the atomic transition that we're looking at, we can change around this collisional systematic. So we haven't seen this systematic yet in this fluorescence, but we're aware that at some level we might have to deal with that. And we can again change the atom that we're probing. Different atoms have different vapor pressures as a function of temperature. And so more vapor pressure means more signal, but it also means more collisions. So potentially, say, potassium might be better for hotter temperatures if the atoms are thermalized at what need to be thermalized at this temperature. And cesium might be better at lower temperatures because it has a higher vapor pressure. Something like that is the expected behavior. Again, we probably want to play around with different atoms because different atoms have different detected blackbody radiation wavelengths. And so which atom you choose is also perhaps a compromise between getting rid of the collisions and measuring the wavelength of interest. So I'm going to wrap it up with this slide here, which is just basically showing what we've done to date and what we think we might be able to do in the future. So with our fluorescence thermometry, it's a very fast measurement. Currently, our sensitivity is about 0.1% per root hertz, right? So that's like 0.3 Kelvin at room temperature in a second. So we're not statistically limited at all in terms of a 1 second measurement. It's really understanding our agreement with theory. If we can calibrate everything in our measurement, calibrate knowing the temperature, then we can get an accuracy of better than 1%, basically limited by how well we know the set temperature. So in order to improve on that, we need to go to an experimental apparatus where the temperature uncertainty is not the limiting factor. And in principle, we could get that down to about 10 part per million, hopefully. If we want to do a self-calibration or primary thermometry, currently we've demonstrated about a 4% uncertainty. If we cheat and say we know the temperature, but using our cesium example, likely this month we'll be able to truly do a primary thermometry measurement in cesium. And if we expect that the theoretical uncertainty of cesium is comparable to rubidium, then we think we'll be around 4% temperature uncertainty there. Again, if we just calibrate the atom in a well-controlled thermal environment, we can probably get this example down to as good as 10 part per million with a bit of effort. Based off of the construction of our vapor cell, we're doing a contact thermometry measurement at 12 microns. But I showed you that there's a list of various wavelengths that could be detected in principle, and they could be detected in a non-contact way by changing to something like a sapphire vapor cell construction or some other material that's not entirely standard. In this initial demonstration, we've done about a 50-degree window above room temperature. Based off the vapor pressures of these atoms, we think we could extend down to at least 250 Kelvin with cesium. And that's without doing any additional techniques to increase our atom number. There are also some techniques that we could explore to extend that range if necessary. I showed you a photograph. It's a very simple apparatus, takes up maybe a cubic meter at most, but there are ways to miniaturize this, and we think pretty conservatively we can get this down to about a liter in the next year or so if we need to. So with that, I'll just thank you for your attention, and I'll thank Microsoft Designer for the nice images that were generated for me, and I'll open it up for questions.
I got a question.
Thank you very much, Eric. That was very interesting. Yeah, if there's any questions in the chat, you can go ahead and type them in the chat bar in Zoom. and we can get those answered. In the meantime, I have a few questions that we can start off with. So one question I might have is when it comes to those dipole matrix elements that are contributing to the uncertainty for that case, is that a matter of like a lot of these some of these types of calculations, it's just not enough computing power has been thrown at these particular calculations yet, and that they need to, it's just a matter of theorists just digging deep into that, or something else?
Yeah, so for something like hydrogen, sure, it could be calculated in principle, from first principles. For something like rubidium or cesium, you know, when you have something like 50 or 80 electrons to think about and all the correlations there, I'm not sure that the theory is ever going to be at the level that we need it to be. The best known matrix elements right now are the ones that have been measured experimentally, and those are usually some fraction of a percent. But for some of the weaker ones, or just the ones that haven't been of any experimental interest to date, right now, I think the theory is at around the 10% level. There's some work right now that is being done at the University of Delaware, where they think they can get down to the maybe percent level in the near future, but that's with modern supercomputers. So I think experiment is probably the way to go, and I'm hopeful that we'll be able to improve some of those values experimentally.
I have an online question. How would you implement CoBRAS technology into NASA passive remote sensors?
NASA process?
NASA passive remote sensors.
Yeah, so there's a couple of possible options here, right? One is the simplest thing is if we were to do a contact temperature measurement, like we've demonstrated, we could just drop it in as a replacement for a platinum resistance thermometer or whatever thermometer is on that device. If we can get it to the required accuracy, but show that it's calibration free and never needs to drift, then that's just a drop-in replacement that's, you know, fit to function. A step beyond that would be to remove the thermometers from the calibration and actually use the atoms to sense the field coming from the reference black body. And then we can use that information to say what the field from the reference black body is when we're calibrating the detector on the system.
Yeah, when see the thermometer purity, we have multiple purity over blackbody, and you know, sometimes blackbody is not uniformly heated. You can detect it. So in your method, you'll be also multiple source for measuring the blackbody temperature. Is that
What was the last part?
you know, in your method, the CoBRAS, the methods, and you're also assuming to implement the multiple measurement over the blackbody.
Yeah, it could be a multi-point measurement. So just by simply changing the frequency of your laser, you can tune the CoBRAS sensor to sense different wavelengths. And we can also swap in different filters on our fluorescence detector to sense different wavelengths from the same excitation laser, like I was demonstrating with the different fluorescence wavelengths. So yeah, and one single sensor has the capability to measure several wavelengths in the you know, few micron wavelength regime.
Thank you. I don't have any other questions online, but if somebody does have a question, you can put it in your chat, put it in the chat.
So with regards to the contact method for the thermometry, replacing the PRTs. So this these fused silica or your vapor cell, what kind of, compared to like the material characteristics of these PRTs, what kind of thermal contact resistance or issues might you run into, or has that been like looked into?
I don't think that's been looked into at all. I think that's a great question. I think that's something that would be really interesting if we were to try to make a PRT replacement device. I think if we were to go back, these sort of fully photonically integrated vapor cell chips are already as small or even maybe a factor of 10 smaller in terms of volume of these PRTs. So something like that could in principle work today if we can figure out how to actually thermally contact it in a reliable way.
It might be, I mean, if there's issues with that, I mean, it might be a better case to make it non-contact, of course, the other method you had suggested. Also, so with your current uncertainties that you're looking at, so like the 1% that you saw, how much is this so far? Is this any of this driven by you know external fields effects that are changing your states versus your detector quantization, how well, or detector resolution of how well you can count number of photons? Where is that largely coming from?
Both of those effects are several orders of magnitude below our accuracy. Those don't play a substantial role in our uncertainty at all. Because it's a thermal vapor of atoms, the sort of spectral window that we need to hit is typically hundreds of megahertz to a gigahertz wide in terms of the laser frequency, and we can control that to within a megahertz or so. So the laser frequency or tuning it to resonance is not an issue at all at this level. And I'll say it's even if we were hitting it off resonance, it's not clear that should play a role other than reducing the size of the signal at first order. So I think any systematic due to the laser frequency, either just because the laser is not resonant with the atom, or because some external field is perturbing the atom, either of those effects would be second order at most and quite small.
If there's no other questions from the chat, I'd like to very much thank our speaker. It was a very interesting talk, and much appreciated. Thank you. Is that
Oh, yeah, that's me. I have a stupid question. See, at the beginning, some bad example.